Is it good? Okay. Okay. All right. Okay, let's begin my lecture about the mechatronics. And I will still give a short self-introduction, although I gave it on Monday. And then I will talking about the robots, Arduino, and probably also the Raspberry Pi because it's a computer. I will give more information later on. And then talking about my research, the multi-robot system. But, well, probably you also need to understand what is the multi-robot system because you may create many software robots because we have 5 fingers on our hands. So if one finger means one robot, and then that will means 5 robots in one group. So there will be a multi-robot system. I'll explain more later. Then we can use Python, which is a computer language. And then I'll be talking about my current research in our lab, which is related to multi-robot systems and also the coordination. And I'll talking about the future work. Okay, so my name is David. Chinese name is Jingwei or Zhuang Jingwei, but international students kind of, so you can just call me David. It's fine, very common name. Just graduated from UC Davis last year, so that's why I'm still a very young teacher here right now. And so for me, I still think I'm kind of a student, like a postdoc instead of professor actually, because I just work on my research or kind of extend my previous research here. So that's why I'm still focused on multi-robot systems. The picture on the top right corner, this is an educational robot I used in the US. It's actually for elementary school students or junior or even the high school students to learn programming, math, and robotics in their schools actually. So we have some kind of competitions to ask them to write a program during the probably 2 hours, and then put these kind of robots on the big huge map, and then try to calculate the distance or the velocity so they can complete some kind of tasks like grab a ball from one place to another place, some kind of this, or parking it to a parking space. Okay, so this is a very simple educational robot I used in the US, but now I use the one at the bottom, this picture. It's a kind of more advanced as you can compare with it. Although they all have a computer, a controller, and also also a camera. And as you can see, we have a very large robotic arm and advanced robot here. And also the wheels are also different. We have 4 wheels in this robot, but in the previous one, we'll have 2 or 3 wheels. Okay, so as you can see, the structure of the robot becomes like more advanced, but they are all robots because they have the same comments. So that's so we may probably try to think what are robots. They can move probably. They can move from one place to another place, so which means they have wheels, and probably they have some sensors like ultrasonic sensors, lidar, something like that, and they may have some cameras, and also probably they have robotic arms. So with these devices, we can create a robot. Okay, so let's see some kind of videos. The first one is a very advanced humanoid robot from Boston Dynamics, which is it's a lab actually. At the beginning, it's a lab in MIT, the very top high school in the US. And right now, I believe it's kind of a company right now because they actually sell these humanoid robots and robot dogs from Boston Dynamics. And this one, as you can see, its title is called the Farewell to Atlas. Atlas is its name. And farewell means goodbye. Switch because it's a kind of an old style humanoid robot. They are going to rebuild the new one with electrical motors. So here is just a kind of a combination of the other videos, the previous videos they created, and then play some and show you guys how this robot can do or what these robots can do. This microphone is broken. I have to hold it like this. Hold on. Sorry. Okay, so as you can see from this picture here, this is a camera on the top actually, and also it has some kind of lidar sensors and ultrasonic sensors in order to sense the environment, like the obstacles as we saw in this video, and you can also see there are many, it makes many mistakes actually, well, like falling down, something like that. And this is a learning process. It's learning process because usually with these very challenging movements, we need to use a machine learning method in order to let robot to learn the motion. So this is they need to test it again, modify the program, and then test it again in order to make sure they can have this very nice movements or performance. Okay, so the next one is called Unitree Robotics, which is a company in China. They also build a humanoid robot, and actually it's very similar to the. Sorry. Actually, it's very similar to this Boston Dynamics, the robots in Boston Dynamics, kind of a advanced one. So we may see the movement like this in this video. Well, in this case, they use all electronic motors instead of hydraulic motors. So the movement might be a little weird compared to the movement in like human, because probably it's not like human. Like this, probably we are not able to do this. Well, they still try to test it because this is learning process. They cannot fall down by any punching or hitting. It has to balance itself. So this process is a learning process. Well, it's a little disgusting actually. It means it's very light compared with the previous one. I believe it's very light. Okay, this is a simulation in order to learn this movement. So that's why they create many robots in the simulator and that it to learn this small movement and then apply this program to the real robot. Well, they can still do the very tiny or detailed task as long as they learn how to do that. We are not to write a specific program to it to ask it to do the welding stuff, but we may just give it a goal, and then it can learn it in the simulator first, and then apply the final version of a program to the real robot, so they can do the very tiny or detailed task. Okay, that one is from the OpenAI. I believe you heard Chat GPT before, and this is a company which created the Chat GPT, OpenAI, and they also built this humanoid robot. It's kind of a more advanced one. It's called a Bigger One, and right now they released a new version called the Bigger 2. It happens just last month, I think. So if you like to watch more videos, well, just Google some keywords, and then you will find more advanced humanoid robots.
I see a red apple on a plate in the center of the table, a drying rack with cups and a plate, and you standing nearby with your hand on the table.
Great. Can I have something to eat?
Sure thing.
Great. Can you explain why you did what you just did while you pick up this trash?
On it. So I gave you the apple because it's the only edible item I could provide you with from the table.
Great. So, based on the scene right now, where do you think the dishes in front of you go next?
The dishes on the table, like that plate and cup, are likely to go into the drying rack next.
Great. Can you put them in?
Of course.
All right. So how do you think you did?
I think I did pretty well. The apple found its new owner, the trash is gone, and the tableware is right where it belongs.
I agree. Thanks, Figure One.
You're welcome. If there's anything else you need help with, just let me know.
Well, in this video, they kind of try to show you that this robot can have a communication with a human. Because it's advanced, kind of advantage in OpenAI or ChatGPT, right? When we type any questions or ask it to do anything, reply to anything, well, they can reply to us. So in OpenAI, this company, they kind of combine the humanoid robot with ChatGPT. So the robot, this robot, as you can see, they can reply to us. But how about the tasks, like grab an apple or throw the trash to the basket and put the cup and plate to the basket? This might be learned from other company, although I'm not sure because I don't work there. But they had, if they create this robot that it can move like this one, they probably still need to practice a lot, which means during the learning process, and also they may need to provide more objects, not only apples, probably oranges, or what else, or some other fruits or vegetables, and then make it and with the trash and put all of them on the desk. So they still need to learn a lot actually in order to have this performance. So as you can see in these 3 videos, we can make a very short conclusion. Okay, we can make a very short conclusion that, of course, they should have several motors, no matter hydraulic motors or electrical motors. So we called it actuators. Or like in this course, we use air pump, right? Probably you will see air pump later. This will kind of an actuator in order to give air pressure to the robot. And like the video, in the third video, the robot can listen to our commands, and also they can reply to us. So they need like sound sensors in order to receive what we say, and also speak to us or pronounce, kind of speak some kind of sentence to us, reply to us. And also they all have several range sensors like LiDAR, ultrasonic sensor, and cameras in order to see what kind of things on the table or us, human beings. And most importantly, I think will be controller and the computers. If without a controller, they are not able to control these actuators, no matter the sound sensors or the motors. And also, we also need computers, because with the machine learning method, there's a lot of computing process inside the computer. We are not able to run the machine learning process in a controller. So at least we need one computer on a robot in order to control all devices, no matter the actuators, sensors, or even the IMU, the gyroscopes or the accelerometers. Okay, so that's why we are going to talk about the controller and PC or computer. Well, we just use a very tiny PC like what you are using right now, the laptop or the iPad. They are all computers. So that's how we connect the computers with our controller. Also, this is a very simple controller for education. It's called Arduino. And you may go to a website down there, the www.arduino.cc. This website to see more information. I may probably show you later on, and also my TS may show you how to write the programs later on in the afternoon. So basically, with this very simple simple board, we all have, it seems we have around 20 pins on this board, and it can provide the digital outputs and analog outputs, also the input actually, or I should say signals, digital signals or analog signals. And what are they? I'll give you the explanation later on. And on the right side is Arduino IDE, the integrated development environment. So we can write the program here inside the Arduino IDE, and then kind of give it a comment through the window, which is called a serial monitor. We will also learn it later on in the afternoon. So don't worry too much. My TS will teach you guys. So right now, I'm just give you some basic information about Arduino. Okay, so talking about the digital signals and analog signals, what are the difference? Does anyone learn this before? Okay, so do you want to explain to your classmates what's the difference between digital signals and analog signals? You want to explain to your classmates?
The digital signal is signal which shapes rectangle signals. Analog signal is shapes like sine curve, right?
Okay, yeah, that was almost correct actually. Let me explain more about digital signal and analog signals. So with the digital signals, it only has high or low. High means 1 and low means 0. So in the circuit, when we give a digital signal with a high value, it will provide 5 volt. Like this diagram, it will provide only 5 volt. And if we give it a low, 0, and then it means we provide a 0 volt to a circuit. So if we connect it to the like a light, the LED light or this one, when we give a high 5 volt and then the LED, we can turn on the LED, it may bright. But if we provide the 0 or low, well, it turns it off. So it only the signals may look like this, not always, but I create this on purpose. It looks like a rectangle, like rectangles. It can just only 0 or 5, not others values. And in the Arduino code, we use these two functions, digital read and digital write. Digital read means we read digital signals, and digital write means we give or provide the digital signals to a circuit. We will see some couple examples later on, and also we are going to use this in the afternoon, and our TS will teach you. So as this class, these students answer my questions, a difference between the digital signals and analog signals. The values can be varied. For example, in the digital signals, it can only be 0 or 1, or 0 volt or 5 volt. But here, it can be any values between 0 volt to 5 volt. So the signal curve made like this one, the sine waves or cosine wave. Well, it's not actually true, but in order to show you the image, I give you a basic image. I should use this sine wave or cosine wave to show you that the values can be 2.5, can be 1 volt, can be 3 volt. It can be any values between 0 to 5. Inside the Arduino code, we use analog read and analog write. It's very similar to the digital one, right? So it's very easy to remember these functions. The digital read, digital write provide digital signals, and analog read, analog write provide the analog values. Okay. So in the Arduino code, the analog read means to receive analog signals. The value will be between 0 to 1023 integers instead of floating numbers. So if compared to the 0 volt and 5 volt, 0 means 0 volt, and 1023 means 5 volt. So if we provide like a 512, well, it may probably provide 2.5 volt to a circuit because the value is in the middle, 512. Sorry, yeah, 512. So with the similar idea, analog write means we provide, not read. We provide the analog signals to a circuit. So 0 means 0 volt and 255 means 5 volt. So with the similar idea, if we give 120 127 is around 2.5 volt. So we can recalculate it back to our voltage, to the circuit diagram. Okay, so this is our big difference between the digital signals and analog signals. It's very important in the control system. Actually, here's a kind of not right now. Later on, I will show you an example later on how we control the devices with analog signals and digital signals. So in this slide, we show you how we communicate with Arduino or with a controller. At the beginning, we use a zero begin. This is a function to set up the communication frequency. Well, you can imagine that it's like a walkie-talkie. Do you know walkie-talkies? Okay. So we may have to switch to a different channel, like channel 1, channel 2, channel 3. And we're supposed to communicate with each other if we are only on channel 1. If I switch to channel 1 and you are in channel 2, we are not able to communicate. So it's the same idea. We set up the same communication frequency. It's called the baud rate, and its unit is bits per second, BPS. It means bits per second. So here is a value for a frequency, like 9,600. There are a couple of other values, but I can't really remember it. We can check it in the official website. If I have time, I will show you later. So we did the same communication frequency, then we may communicate with Arduino code. So, okay, so in the first line, the Arduino is still waiting for comments from the user. After the Arduino receives a comment, it will read a string. And then if a string is on, you can see it's a word or not 2 letters, actually. So if the Arduino receives on, then it will print out on, the capitalized on, And if the Arduino receive the off, this string, and then it will print out off, capitalized off, OFF. So if in the afternoon, well, probably we can test this program because my TS will teach you how to use Arduino to control the air pump and relay in order to control your software robot. And communication is also important because we can print out information in the serial monitor. Okay, so about control, well, as we mentioned, the analog signals and digital signals, well, here we provide digital signals here and analog signals down there. So at the beginning, well, we still need to give the baud rate, which is a communication frequency with the same value, just to make it simple as possible. And then we set up the pin modes. Here, output means provide signals, not receive signals. If we want to receive signals, there will be input. And here we want to say as output because we want to provide the digital signals or analog signals. And 13 and 11 are pin numbers. TS will explain more later on. Okay, so with a very similar concept or the structure, the Arduino will still wait for any messages or commands from the user. And if it receives 13, then you will provide the digital signal with high means a bivolt to the circuit with 1 second. So here I use an LED as an example. If we write like this, which will give it the digital signals to the circuit, we may turn on the LED for 1 second. And then we turn it off because low means 0 volt. And later on, if we type 11 to the Arduino board, you will give the analog signal to the circuit. Here, I would like to use analog signal because we want to control a DC motor. For DC motor, when we apply like a 3 volt, well, it can rotate, right? If we provide 6 volt, it can also rotate, right? Unless they still have the range actually from probably 1 volt to probably 13 volts. But in between, it can rotate no matter what value is. So in this case, we can provide analog signals to it. And here, I use 127. The reason I just mentioned before, we just give it half power to this DC motor. See, so it won't speed at the full speed. It only speed at the half speed. And then you will rotate like 2 seconds, and then you will turn it off. So this is how we control our soft robot actually. So our TS will give you more information like this in the afternoon to see how we control this soft robot. So we won't blow it up. It's very easy to blow it up. If you use your air pump by hand, you may see how it can expand. But with a controller, you may have to be very careful. Do not give too much air in the soft robot, or you are broken, and then you will have to create more. So that's why I say it's better to create more soft robots, and then finally, in the end, we may build a multi-robot system if we see one soft robot as one robot. Okay, so from a single robot, well, I probably mentioned a lot. From single robot as one software robot here, it might be very simple like the previous case. We just write one Arduino code and then we can control one software robot. Well, it's good, nice. Very simple. But how about the several robots, which means we have several software robots. We have to control 3 fingers at the same time. What should we do? Can we just use one Arduino controller board to control 3 software robots? Probably yes, but a little challenging. But if we have a computer and with several controllers or several Arduinos, probably this will be a little simpler to do it. So that's why we have to involve a computer here in order to control many robots. Before talking about the control system, I would like to give you a very, very simple background about the multi-robot systems. We can classify them as homogeneous or heterogeneous multi-robot systems. As you can see in these 2 diagrams, on the top one, these robots are all the same. They all have wheels, have a robotic arm, and probably have some sensors, but they are all the same. But for the group at the bottom, some of them can fly like a drone, or like a submarine, or water surface vehicles, or boats. They will be different. So in this case, we will call it a heterogeneous robots. So if you create different types of soft robots, then we will say will be a heterogeneous multi-robot system. If you use the same mode to create your soft robots and with totally the same manufacturing process, well, we can say all of them are the same, and that will be a homogeneous multi-robot system. And in the another one, we call it a centralized or decentralized. Centralized means we use one computer. As I mentioned a little bit before, we can use one computer to control many robots. They can be the same, they can be different. It doesn't matter. But we use only one computer to control these robots. So if possible, well, you can also try it during these 2 weeks. If we have several Arduinos, several air pumps, and then Arduinos, and also Arduinos, then we may build these centralized remote robot systems if we have time during these 2 weeks. If not, well, it's fine. The TS probably will show you in the end because they want to create a hand with 5 fingers, and that will be multi-robot system. And in that case, we can use a centralized control system to control these 5 fingers. And the other one will be a decentralized, which means each robot can make their own decisions. Like previous humanoid robots, they use one humanoid robot. So how about we put 2 humanoid robots together? We can create a robot team. Well, they are independent, but they can still communicate with each other. So in that case, you can see that there's no central computer. So there will be a decentralized system. Like this ground robot may communicate with a drone, and also the 2 ground robots may communicate with each other. And in this case, we also call it distributed multi-robot systems because they can freely communicate with each other. The broad idea about the decentralized means like this one, the arrow to these tiny robots at the bottom right corner. There are another group, and this huge diagram is one group, and the other tiny robots are another group. And only 2 robots can communicate with each other between these 2 groups. So in this case, we call it a decentralized system. Okay, and then in order to create these structures, as I mentioned before, like the decentralized or this centralized system, we use a middleware, which is a technical term to represent the software structure. We call it a robot operating system, or ROS. So this is what I'm doing in my lab. We use ROS, this software, to communicate with several robots or devices in order to control all of them. So this is an open source platform that we can use it to control many robots. So that's why I would like to use ROS, this system, to control many robots. But this is very difficult. It's very challenging. We are not able to use it in this course because we only have 2 weeks, but actually 1 week. We may learn it around a month, or probably at least 3 months, probably. So it's impossible to apply ROS, this system here. So that's why we use a kind of simple program with a centralized system with our data. So we can control 5 fingers or 5 soft robots. Okay, so we must use Python because we have a computer, and then we can use this Python code to control many robots in ROS. Although we are not using the ROS platform, but we can still write a very simple Python code to control many software robots at the same time. So how do we control them? Well, communication is very important. So as I mentioned before earlier with Arduino code, we need to have the same channel. So here I also use a 9600 as our baud rate, or channel 1. And if we type another one like 10,000, that will be channel 2. And also we need to give it the correct port name. Here is called the COM4. You may probably have a different port name, but it's totally fine. You will learn it in the afternoon. The RTS will teach you how to find out the correct port name. And after the computer connect to a controller, I would like to say computer and controller. And because Arduino is one of the controller, it's not always the Arduino. We can use some other controllers to control the electronic devices, but with the same, almost the same concepts. And then, if we remember the previous Arduino code, if we provide 13 this string as our command to the Arduino, then Arduino will do something inside the Arduino code and then reply to us. So here in this line, we can receive a message from the Arduino or the controller and then print it out. And with the same idea, we can also provide the other command or another string to the controller or to the Arduino. And then the Arduino will do something and then print out this or send another message to the Python here and then print it out. And finally print complete this sentence. Okay, so what will happen if we give 13 and give 11 to the Arduino? Well, we have a simple code here. I hope you remember this. When we type 13, it will turn on LED. If we type 11, then we will turn on the DC motor. So with the same idea here, if we enter 13 in the first part, the Arduino should turn on the LED. And if we type 11 here down another part of code, it will turn on a DC motor. So here I try to compare with each other. First of all, we write this Arduino code to the Arduino, and then we run this Python code on our laptop, on our computers. When we run this Python code here, we will send 13 this message to Arduino. After Arduino read this string, you will recognize that, oh, the string is 13. And then you will turn on the LED for 1 second. And then after that, you will print done or send this string back to the Python code. So in our computer, we will receive the message called done here. And after that, for another part, I just want to give you 2 examples. That's why I separated. If we give 11 this string to the Arduino, well, we send this message to it. Well, Arduino receives it and then find out the 11. So the Arduino, the controller will control DC motor for 2 seconds and then print done and back to the Python code. So this is how we communicate or how we control controller with Python code with our computer. So that's why in order to build a robot, we need 1 computer at least. 1 computer and 1 controller and some other devices, actuators, sensors, even cameras. So communication is very important. Oh, so far we only control 1 robot actually. We send it's 13 to 1 Arduino, send 11 to 1 Arduino, and then receive any feedback from Arduino. Here we only control 1 robot. But how about 2 robots? Kind of simple, right? Let's assume that we have 2 Arduinos. If we have 2 Arduinos, well, with the same idea, we need to set up the switch to the correct channel, like channel 1 here, for simple. But the port name will be different. It's based on the, each person may have a different port name, so we have to check it out. Our TS will show you how to find them in the afternoon. So here we have an Arduino 1 and Arduino 2. And then we send 13 this message to 2 Arduinos or 2 controllers. So the 2 controllers can have different programs. If they receive 13, the Arduino will do some kind of stuff like turn on the LED or turn on the DC motors or turn on the air pump, for example. Well, they can be different. And then we will wait for any messages or feedback from Arduinos or controllers, and then print the messages out. So this is how we can control several robots or several controllers or devices with Python code with our computer. So that's why we need at least one computer. I would like to mention or emphasize several times. At least we need one computer, one controller, and some other devices in order to create one robot or control one robot. Questions? This is very important for in this course because you are going to use them, all of them, in this afternoon to control your software robots. And don't worry too much because our TS will teach you how to write these programs. And also I provide my slides on the website, right? So you can also download it and try out in this afternoon. Okay. Oh, so this is another part. Sorry, I forgot. I have to separate two parts. This one we send the 13 to two Arduinos, and the next page we send 11 command to the another two other Arduinos. So with the same idea. Well, although we don't know what will Arduino do after we send 11, we're supposed to write a code to Arduino first. But these two codes can be different. They are not the same. Not necessary to be the same. They can be different. So different controllers can read different signals or control different devices. Depends on our purpose. Okay, so in the end, we print out the complete at the end. Well, so this is how we control many controllers or many robots. Okay, so far so good. What time is it? I just want to see how much time do I have. 9:50. So only around 30 minutes. Okay. Let me give you a very quick, brief idea about my current research, not related to this course, but the research topics in my lab. Just give you a basic background. Okay. My research is related to multi-robot task allocation. This is how we assign tasks to robots. Because right now we have several robots, not just one robot. We have several robots. So here's an example like a birthday party. In a birthday party, we have several things to do, right? Like buying a cake, buying some foods or drinks, or someone should take some pictures, or I can show the decorations. I just use this symbol, fireworks or decorations. Some of them should go to a store to buy this stuff. But who should take pictures? Who should go to a store to buy a beautiful cake? Or who should go to a supermarket to buy some decorations or drinks or food? Who should do this? How do we assign these tasks to classmates or to your friends? With any factors or any ideas how we assign these tasks to your friends? I'm not talking about the robots actually, but I would like to use this example to show you how we assign tasks to robots. But it's the same idea. These are all tasks, right? In human beings, we can see our as robots. So that will be a multi-robot task allocation problem. Any idea? No?
Like for example, people who live near the supermarket.
Near
should
supermarket.
go buy the stuff from
Okay, sounds good. But how about the money? Oh, I'm living near the supermarket, but I have no money. So how can I buy money? How do I buy this cake or drinks or food? Well, right. We have several factors we need to think about. So like taking pictures. Well, at least I need to have one camera to take a picture. So probably you may think, oh, we can borrow one from another. Okay, it's fine. But for me, I won't be a photographer because I'm very bad at taking pictures. So I should find out one professional person to take a picture, so we can take a beautiful pictures for our the main person. Okay, so we can assign this task to some kind of to these people based on their skills, like buying if they have money or like they live nearby the supermarkets, they can go to buy cakes, drinks, foods, or decorations. And if they are good at taking pictures, well, they can take pictures for people. So in this, based on this idea, well, you don't need to learn this too much. It's our idea in my lab. The basic idea is using the success rate in order to assign tasks to robots. This is a simple structure we created. We will modify it later on in my lab. Not you guys, it's in my lab. And then we can assign these tasks based on the success rates. So if the robot can complete this task with a higher success rate, probably it can take, or it should take the task with a higher success rate. And in order to find out the optimal solution, we set out the sum of the total success rates. So if the sum is higher, well, we can find out the better solution, and then we may assign this task to robots. So this is our main concept in our research in my lab. Well, you won't use this in this course. I just want to give you a very simple background about this. But this will be kind of important in your daily life. Probably you will have it happens a few days later, probably. So you may think about it. Okay. As I mentioned at the beginning in my introduction, we use a very simple educational robot called LinkBot on the left side here. And we need a computer, remember? We need a controller to create one robot. So we create this robot like this one. And then in this case, I did this in the US. We use several robots, 6 robots. They are kind of a little different. And then the 2 car targets in this rack, because it's a search and rescue mission in the terrible house. And then these 2 targets, we're supposed to move these 2 targets out of this building because of power earthquakes, and it becomes a very bad condition. So after this sum of 3 robots detect these 2 targets, then we access on some other robots to move these targets out of this building. This is a decentralized system or distributed system instead of a centralized system. And then they all have different skills. So based on my method related to success rates, we can assign some of robots to these tasks properly. Okay, in the other case with the same situation, but I make one robot fails on purpose. So I just quickly use my hand to make it lay down. And then there are some other robots can still or should still complete the rest of tasks and do the same thing. Our goal is to move these yellow targets out of this building. So as you can see, very similar to the previous case, even though one robot fails, other robots can still complete this task based on our approach. Well, I'm not going to give you too much details about my method or algorithms because it's a little complicated for you guys. But if you are interested, well, after you graduated from the college and then get into a graduate school, well, you can learn it. Okay, so for now, we have a kind of a more advanced robots right now. But of course, in order to create a robot, at least we need a computer. In the center, it's called JSON Nano. It's a very high advanced computer compared with the Raspberry Pi. And then we have some devices like LiDAR and motors. I'm not able to find out the pictures, so I use this diagram to explain how the robot moves. These 3 tiny stuff means the wheels. And if we have a control board to control these 3 wheels. and then we can make it to straightforwardly going to right direction, going to down directions, or it can rotate. It can also go to the diagonal directions. So it's we call it the Omnibot actually, it's because it is called the Omni wheels. So we still have a computer, a controller, and also some actuators or sensors to create one robot. Okay, so in this video, this is what we do recently. This is taken from it was taken from one of my graduate students, and the main purpose is to explore this map. And this some of sorry, hold on. These boxes are obstacles, but at the beginning they don't know them. They have to use the LiDAR sensor in order to sense the surrounding, in order to explore this environment. So actually, at first, they don't know where the obstacles are. They need to use the LiDAR sensor to sense the environment, sense the rain, and then it will direct to the some of certain points in order to explore the whole map. The basic idea is still using the successful rate, but I'm not going to give you details because I didn't publish my current research right now, so I'm unable to explain anything related to this experiment. But I can tell you some kind of future work that we can move this or change these locations of the obstacles to any places, and then they can still complete or they can still explore the whole map to find out the locations of these obstacles with the success rate. This is our main idea about this research. Probably this is some of sounds from the video. Okay, it's fine. Okay, so here you can see this diagram at the left side. These are two maps from two motors. From two robots. This is a ROS system. Well, as you can see, it's a little very high advanced platform. So that's why I'm not able to teach you here. But you can try to combine these two maps. You can try to combine these two maps. Here means it's not explored. And the empty one, the white means is not map. So if we combine these two maps, we can see that although for this robot, the robot on the little right corner, that one, it cannot see the map on the right side here. But for another robot, the near one, it can see this area. So by combining these two robots, these two maps, we can explore or we can find out the whole map for this environment. So we complete the exploration mission. Okay, so in our future work, I'll show you some other videos to see what we can do with several robots. And this warehouse, which means we kind of move some parcels or packages inside the factories or logistic house, and then with several robots, and then we may increase our efficiency, working efficiency.
AMR and AGV robots are used across many warehouses and distribution centers today. Robotic automation improves employees' productivity, speeds up order fulfillment, and drives customer satisfaction. AGV robots have been around since the 1960s. AMRs have become popular in the last decade. So what's the difference between these two robotic systems? Automated guided vehicles, AGVs, are unmanned load carriers, directed by software and sensor-based guidance systems. AGVs follow a pre-established path, using permanently fixed magnetic strips and LiDAR for guidance. In that sense, an AGV is more like a train than a car. If something blocks its path, the robot will stop and call for help. They are mainly used to transport larger and heavier payloads and are best suited for environments that don't change often. Unlike AGVs, autonomous mobile robots, AMRs, can choose different routes to travel to their destination. AMRs are more flexible, which makes them more suitable for dynamic environments, where requests are constantly changing. One example of AMRs is in Via Picker robots. These robots use machine vision with fiducial markers. They can detect the position and orientation of fiducials with ultra precision. By sticking these markers on warehouse shelves, robots can easily localize themselves. Their sensors enable AMRs to detect obstacles and automatically navigate around them. Software remapping can change the paths of the robot without a need for extensive changes to the infrastructure. Because of that flexibility, AMRs are widely used in e-commerce fulfillment, where new orders are coming in all the time. So which one is better for your warehouse or distribution center? Although AGVs and AMRs can both be used to transport goods within your facility, they have quite different warehouse applications. The AGVs are most often used for larger, heavier payloads that need to be moved along the same defined path. AMRs are much more flexible and intelligent in the way they navigate the warehouse. They are optimally used for order picking, replenishment, and transporting boxes rather than large objects.
Okay, let's stop here. Well, we call it different. The difference between the AGV and AR is like a defined path. If we have a predefined path, well, we can call it like a AGV or AGV, yeah, and AGV, yeah. And then if they don't have a predefined path, they can bind the path on themselves. Well, we call it a AMR. So in my lab, we use the AMR instead of AGV. And then we would like to build a distributed or decentralized system in the warehouse system because some of them might not able to communicate with each other. So in that case, well, the whole function or the whole robot team might not work properly. So in our future work, we use the MR to complete this warehouse system and with a decentralized system. Okay, because of time, so I believe I have to move on a little quick. And another one is, this is a very old video, but I would like to show you how two robots can collaborate with each other, like in the transportation. We can move one object with at least two robots to move this huge, heavy object from one place to another. For current research so far, I'm waiting for the video. Okay, so far we can see there's a leader in front of another robot. We call it a leader, and the other one is called a follower. So far, the current research just use a leader follower method to control these two robots to move one object, and then if this sorry and if the leader fails or probably it cannot detect this obstacle, well, it may not turn and the mission fails. So in our research in the future, we would like to make it a distributed system or decentralized system to make these two robots independently. They can still communicate with each other and sensing the environment, but if one robot unable to sense, probably we can ask for another robot to sense the environment and do the same job. So that will be our main purpose in the future to build a distributed system, multi-robot system, and move the object from one place to another place, and also avoid any obstacles. Well, here we also need a machine learning process. Well, this is a little challenging. And also, right now, the computer is very powerful, so we can apply a machine learning method to do the task like this. I'm not going to finish it. Okay. The next one is
So much emerging technology is just a show. So one can
taxi.
being able to distinguish fact from fiction. Take this car, for example. Can it drive autonomously or not?
The short answer is absolutely.
That was Shweta Shrivastava, Senior Product Lead for Driving Behavior at Waymo.
What you're looking at is the Waymo driver in action. Adapted for a variety of vehicle platforms, it is the most advanced, fully autonomous driving technology in the world today.
What you notice pretty quickly is that these aren't normal vehicles. Take this Jaguar I-Pace, for example. It's been equipped with an elegant array of sensors and software, which allows it to move through the city on its own.
That's correct. The Waymo Driver is a combination of custom-designed hardware and software that is responsible for performing the entire act of driving.
That was James Philbin. He's an engineering lead on the reception team at Waymo. I asked him to break down the technology for us a bit more.
The Waymo Driver handles the task of driving in 3 basic steps: sense, solve, and go. It's the way we describe the highly complex process of acquiring information, processing it, and moving through the world safely.
So, what goes into all that sensing?
The sensors that the Waymo Driver uses are incredibly powerful, using a combination of LiDAR, cameras, and radar. It can see up to 3 football fields in any direction and can detect sirens from emergency vehicles, which allows the Waymo Driver to visualize the world around it in milliseconds to a high degree of accuracy.
Okay, sense makes sense. But what do you do with all that data?
So let me stop here. So as you can see so far in this video, for an electronic or autonomous vehicle, it also has a computer, although it didn't show it, but of course it has a computer. And it also has some kind of controllers, probably many controllers, because it has 4 wheels and it has LiDAR sensors, what else? Cameras. So can we tell or can we say is a robot or not? Kind of yes, right? Although it's like a vehicle, not a robot. But actually, we can still say this is a robot. If we are in robotics, well, in a broad definition, well, we can say it's a robot instead of vehicle. So in our future work, well, it's a taxi, only one taxi, autonomous taxi on the road. But what if in the future we have several taxis, self-driving taxis on the road? How do we assign these taxis to the passengers, to the required people? They need to move from one place to another place for walking or traveling or trips. So how do we assign these self-driving taxis to the location? Well, this probably will be our future work. Although these are not robots, they are vehicles, but we can still do that with our methods. So this is one of our future work in my lab. Some of the graduate students might need to do this in the future. Okay, so I'm not sure if we have this self-driving taxi in Japan. Do we have it? Probably not, because it's very crowded on the road. And in the US, as you can see, there are not many passengers or pedestrians or cars on the road. The environment is a little simple, but if on the road in Taiwan or in Japan in a very crowded environment, well, it might be very challenging. So, well, it's still like an experimental situation right now. But actually, it's one company is working on in the kind of not in the urban, not in the city, in the countryside. Okay, so
Good question.
okay, so this is what I have for this lecture in the morning, and in the afternoon, our TS will teach you how to use a computer, laptops, and Arduino's controllers to control your software robots. Okay, what time is it? 10, 20, 14. You didn't stop me. Yes, you should stop me.